Hello everyone, and thank you for taking your time to watch this video. And I'd like to tell you about our approach to tackle collusion in secret sharing. This is an extended version of the talk that I gave on ACM CCS 2024, and it's joint work with Stefan Dziembowski, Sebastian Faust, and Tomasz Lizurej. Let me start by recalling how the standard secret sharing works. In secret sharing, we have a dealer and some shareholders. And the dealer, based on the secret S, computes some shares as 1 up to Sn. And the shares have the following property that any group of two parties can always reconstruct the underlying secret, whereas any smaller group has no information about the secret. And usually when the parties do reconstruct, it happens in some implied circumstances that follow from some wider context in which the protocol is placed. Essentially, the shareholders promise that they will only reconstruct under such and such circumstances. And if they do violate this promise, which we will call collusion, then the dealer has no security whatsoever. And in this work, we ask ourselves the question whether there's anything that can be done to alleviate the situation. And the issue of collusion and secret sharing is a fundamental one, because if the parties decide to conspire against the dealer behind his back, then there's nothing that can prevent them from just staying silent forever. And what's worse, the dealer might not even know that the collusion happened unless there are some observable consequences of that, in which case it might already be too late. And the main tool that we use to circumvent this issue is to provide the parties with economic incentives. And we engineer a situation which is somewhat similar to a prisoner's dilemma, and essentially encourage the parties to speak up. And we make sure that the parties will actually snitch on each other if they are rational and act in their own self-interest. However, such a perspective already poses another challenge, because if the dealer is economically minded, he can try to frame the shareholders and try to steal their collateral by convincing the judge that they conspired while in fact they hadn't. And so since we need some consensus regarding whether the parties are punishable or not, we're going to use a trusted judge, of which you can think of as a smart contract on a blockchain. And the two important properties of the judge are that he has a public state, which is important because the parties need to have a common view regarding whether it's legal to reconstruct or not. But the judge still has the power to punish the parties, for instance, by confiscating their collateral. And the example workflow would look like this: that initially Alice and Bob deposit some money with the judge, and only then does the dealer share the actual shares with them. And in case an illegal reconstruction occurs, one of the shareholders, say Alice, will get a proof of that, and she will be able to snitch to the judge, who, upon validating this proof, can confiscate Bob's deposit and, for instance, send a fraction of it to Alice. And before we get into the actual construction, let's take a step back and think about how we can model such situations. And usually in cryptography, we think about parties that are honest, which means that they completely follow the protocol, or corrupt, in which case they might deviate from the protocol. And in a standard secret sharing setting, it might be Bob who's corrupt, or maybe Alice, but it's never going to be the case that both of them deviate from the protocol. However, this doesn't really capture the scenario in which we are interested, where everyone is economically motivated and might deviate from the protocol whenever it's profitable. And the perspective from which we see this is something that we call a coalition threshold. And if Alice and Bob form a coalition, then they will never act against each other, whereas if they don't, they can never be sure whether they will always be loyal to each other. And this is actually a really strong guarantee in the rational setting in which all parties are selfish and will stab the other in the back if given the right incentive. This perspective generalizes really well to the multiparty setting in which the corruption threshold perspective is the standard assumption of the honest majority that you know from various multiparty schemes, whereas the coalition threshold is a much weaker assumption that there is no coalition that fully trusts each other, spanning the majority of the parties in the system. At a formal level, we need a somewhat more sophisticated adversarial model because the standard one, in which there is just one adversary corrupting all the dishonest parties, does not really model what we're trying to have here. Because the adversary cannot be expected to snitch on himself. And this is why we use the distributed adversarial model, in which we have several sub-adversaries, where we assume that these sub-adversaries are truly separate entities with their own interests that might act against each other. In a sense, those sub-adversaries might be adversarial to each other if the incentives are right. And we also assume that the sub-adversaries corrupt not too many parties, because obviously, if you have an individual adversary who individually has more shares than a threshold, then fundamentally there's nothing that can be done. And this is an abstraction that captures two most important scenarios that we're interested in. The first one, in which the parties are just separate actors with their own self-interests, in which each sub-adversary is essentially the same as the party, or in which the parties are Sybil identities. Now, what should such a secret sharing snitching scheme entail? First of all, this is a secret sharing scheme, so if the shareholders are honest, they should always be able to reconstruct the underlying secret. And punishability means that whenever you do a dishonest reconstruction, you should get a proof of collusion. One of the shareholders should get it. And when this shareholder sends this proof over to the judge should accept it. Now, the subtlety is that the dishonesty, the illegality of the reconstruction is in the context. And we cannot only output the proof if this context changes. So what we do is that every reconstruction yields a proof of collaboration. It's just that if the reconstruction is allowed, this proof of collusion is assumed to be harmless. And a final crucial property is unframeability, which means that if I play honest, then I will never be punished. And this is very important because the main idea here is that you will stake some money to guarantee your honesty. And if I could lose my money, even if I play honest, then I would never participate in such a scheme. Now, we do not have an explicit secrecy requirement here because this is already implied, and I will outline the intuition now. The whole point is that if we think about just recovering the full secret, then punishability essentially means that if I get to know the secret, then I can punish someone, and I can punish someone else than myself, because it always takes two to collude. However, the unframeability requirement means that if everyone except me is being honest, then I cannot punish anyone else, and this yields a contradiction. And while I have only discussed the intuition regarding the full reconstruction, we extend it to the setting in which the adversary would only learn partial information about the secret. Why would such a secret sharing snitching scheme be useful? Well, usually those implied circumstances when the shareholders should reconstruct are some event. And the idea is that they only reconstruct after some event has happened. And this can be anything that's publicly verifiable. So you can consider the height of the blockchain, which is essentially a proxy for time elapsed. You can count some votes cast in an election. You can track the transfers on a blockchain. You could even consider that the reconstruction is only legal after some exchange rate hits some threshold. And the nitpick here is that we can only consider the first time until it's happened, because after the reconstruction has become legal, it should remain legal forever. Another cool thing about our scheme is that in some cases it can provide an alternative to time-based crypto. And a very inconvenient property of time lock puzzles is that you need to estimate how fast the adversary is. And this is quite error prone. And in our scheme, if you think about the blockchain height application, there is no need to do it. And moreover, the cost is asymmetric, as you will see, and it's asymmetric in the right direction, because for time lock puzzles, the cost is also asymmetric. But if you want to be sure that your puzzle takes at least an hour to be solved, then you should assume that the adversary has more computing power than the honest parties. And for instance, the honest parties would have to work for 3 hours, for example. Whereas in our scheme, as you will soon see, the dishonest parties bear a higher cost, because they would need to run the whole reconstruction using secure multi-party computation in order to avoid being punished, whereas the honest parties only computed on their own hardware directly. However, the disadvantage is that you only get game theoretic security by using our scheme. Another interesting application that our scheme could provide is the prevention of front-running attacks. It's something called minor extractable value or sandwich attacks. And in front-running attacks, the miner abuses the knowledge of the transaction submitted by an honest user of the blockchain. And you suppose that the user submits some exchange transaction, which will cause a fluctuation in the asset price. And if the miner knows this transaction, it can submit two transaction of his own that would grant him a risk-free profit at the expense of the honest user. And there are various approaches regarding how to deal with that, but one approach could be that the user simply uses secret sharing with snitching to share the transaction details with a committee who would be responsible for the reconstruction of the transaction data, and only shares a transaction commitment with a miner. And this means that the user is protected against the collusion of the committee, whereas a committee can be held accountable for reconstructing the transaction data in a different way. Now, let's try to get to the construction. And a strawman idea is to simply try to augment the shared secret with some punishment data P, and share the augmented secret with the shareholders, with the idea that the judge would punish whenever someone submits the punishment data. However, this scheme has two issues. And first of all, the dealer knows the punishment data, so they can frame an honest shareholder. And there is another attack that the shareholders might try to do, is that they can try to run the reconstruction in MPC and discard any incriminating data. And this means that on one hand, we need to have some notion of MPC hardness to circumvent this issue. And the consideration of multi-party computation as an attack vector is one of the novel aspects of our research. At a formal level, what we assume is that massive computation of hashes like SHA-256 is impossible, and to model this, we will consider a random oracle with two modes of operation. And there are fast queries in which the party individually asks a random oracle about the hash. And in this case, the input and the output is fully known to the party. And there are slow queries, which are essentially MPC evaluations of the hash function in which none of the parties knows the full input, and each of the parties gets to know the full output. And the key security assumption here is that there is a bound on the number of slow queries, that is, the hash evaluation over MPC that our adversary might do. And the intuition here is that there is some implicit time constraint for the evaluations of the hash function, and the adversary will not be able to compute so many hashes in MPC because they will simply run out of time if they try to. And the formal level is somewhat tricky because this number could actually depend on the security parameter, but no adversary can do more than a polynomial number of queries. So sigma is a fixed polynomial, and the honest parties will run, and all the parties can have an arbitrary polynomial number of fast queries that can depend on this bound sigma. And in our construction, we will start by building a 2 out of 2 scheme, and then we will compile it into a threshold scheme. So now let's take a look at the real protocol. So all the parties start by sampling some randomness, and they run some multi-party computation functionality. And in here, we are using this assumption that I have not really stressed before, but it's an important thing, that actually computing a few hashes in the MPC is feasible. It's just a massive computation that's impossible. And what the shareholders do is essentially that they first share a random secret, X, and then they concatenate it with the dealer's randomness, compute a hash, and send this hash to the judge. And afterwards, the dealer can use his own randomness to encrypt the secret. And notice that this Y is short, which basically means that once the parties have reconstructed their random secret, then they can just use brute force. So the actual reconstruction looks like this. Say Bob sends his own share to Alice, and Alice will then just reconstruct X, brute force the hash to find the pre-image of Z, and use the value Y to decrypt the message that the dealer broadcast. What's the intuition for snitching? So the proof will be just the pre-image of the value that the judge received. And the main intuition here is that unless you have reconstructed this shared secret of the shareholders, it's infeasible to brute force. Why? The point is that X is long, it's around kappa bits, and Y is logarithmic. And on the other hand, the dealer doesn't know this long shared secret of the parties, which will yield unframeability. However, if the parties would like to escape the punishment for an illegal reconstruction, they would need to run this whole brute forcing entirely in MPC, and we have already assumed that such a massive hash computation is infeasible. And so the snitching phase is quite simple. The Alice will just send the pre-image to judge, who will check if it's the right thing and punish the other party. Now, This is not yet the real protocol. So for instance, the adversary might be lucky while brute forcing. And another issue is that this Y is short, so we cannot really use it to encrypt the secret. But the solution is quite simple. We just repeat what we have, what I have showed you in parallel uh, enough times. We use all the randomness of the dealer to encrypt the secret, and we use any preimage as a proof of collusion. And if you think about it, then the same protocol actually works in an out of n case. Now, the threshold scheme. So I have already mentioned that we want to be sure against all the collision that are not just trivially impossible, that is, of collisions that have size less than t. And the idea here is that we would like to use use standard Shamir secret sharing on any other scheme, secret sharing scheme of your liking to get the threshold functionality, and our scheme that I have presented in a while ago to get snitching. And actually, a cool thing about the construction is that this allows a fine-grained identification of the traders. And a Strawman idea for the threshold scheme is to just first do a threshold sharing and then share the pairs of shares using secret sharing with snitching. But this is actually not secure when you consider trustful coalitions. And the reason is such. If you have pairs of parties that fully trust each other, then they can first do the SSS reconstruction and do it with impunity because they form a coalition. And then those coalition can engage in a threshold reconstruction, but the threshold scheme does not know what snitching is, so they do it with impunity. And the solution here is to just do this threshold sharing twice. So in the real scheme, we start with the first level of threshold sharing, then we do another round of threshold sharing, getting such a matrix of shares, and then we will share pairs of shares between the shareholders. And now the intuition about punishability is that if you want to reconstruct the secret and you participate in this reconstruction, then you need to get t values from your column. And since each row of this column was shared with a different party, you need to interact with t distinct parties, including yourself. But the collision size is less than that, so you need to involve an untrusted party, so one of you will be able to snitch. And thank you for taking time to watch this talk, and you can find the full paper on ePrint. Thanks.